Okay, so today we are going to talk about angular momentum. Okay, so we'll talk about two sort of related things. Okay. First thing we'll start off about talking is rolling motion. Okay, and you guys have all seen objects rolling. So here's a wheel that is rolling. Okay, and a rolling motion turns out, which you'll see in a second, is pure translation plus pure rotation. Okay, so what that you'll see that in a second. Like I said, here's a pure translation motion. If every point on this object is moving with the same velocity, and pure rotation is, here's an object that is fixed and it's rotating about that axis. So a rolling motion is the sum of these two motions. So that's what we'll learn the first part of this chapter. Okay, and the second part of the chapter will look at Newton's second law of motion. Okay, so here was Newton's second law of motion for linear motion. Force was equal to rate of change of linear momentum. Okay, so what you will see in this chapter is torque is equal to, the parallel equation is for rotational motion is torque is equal to rate of change of angular momentum. Okay, and then we'll see applications of this equation. So this is Newton's second law for rotational motion, and you'll see that torque on a system is equal to torque due to internal forces. And again, I'm just giving you a preview of the chapter. We'll go over details. Is internal torques due to internal forces, and then torques due to external forces. And you'll see some cool applications of this equation is equal to rate of change of angular momentum of the system. Now this is always zero because internal forces always come in pairs and their torques will add up to zero. So in a system, it's external torques that changes. For a system, it's the external torque that changes the angular momentum of the system. And oftentimes this is zero. Okay, so when this is zero for a system, its angular momentum is constant, so L will remain constant. Okay, and we'll see some spectacular applications of that. Okay, all right, so that's some of those are two of the main things that we'll be covering in this chapter. We'll start off by looking at rolling motion, and then we'll look at Newton's second law for rotation. Okay, so that's what this chapter is about. All right, so let's so here are the topics we'll cover. So as I said, rolling motion. We'll start off with rolling motion, which is a combination of translation. We'll define angular momentum denoted by L. Conservation of angular momentum is what I just stated. When external torque on a system is zero, when there's no external torque acting on a system, the angular momentum of the system remains constant. And we'll look at some fun toys like gyroscopes. Okay, so let's start it. Okay, so let's start with rolling motion. Hey guys, one question. It seems like some of you guys you enter the classroom and then you're kicked out or something. Is that happening often? And did you just get kicked out of the room and then came back in? Okay, anyway, okay, so getting back to this. So rolling motion. Okay, all right. So rolling motion is, so so imagine a wheel, and this would be pure translation if this wheel moved like that. See, every point on the wheel has the same velocity, and this entire wheel is being transported to the right. Here's a wheel that is spinning, and it's spinning about that axis. So these points are moving in this direction, these points are moving in this direction. So this is an instantaneous snapshot. So the wheel is spinning like this. This wheel is just moving, translating to the right, and this wheel is spinning like that. Now, if we combine these two motion, and when we say we're combining these two motion, what we're doing is we'll take the velocity of each point and add them up. So add this velocity plus this velocity, that's what you get. This is the center of mass velocity plus this velocity is that's what you get. And when the wheel is purely spinning, see, opposite points are moving in opposite direction. And this velocity plus this velocity will give you 0. Okay. So in a rolling motion, so this is the ground. When a wheel rolls, it's really a combination of pure translation and pure rotation. And that's what this slide is showing you. Okay. Okay, so here's a picture of, oh, by the way, so hang on a second, let me. Okay, so here's a picture of a wheel that is rolling, and as it rolls, so there's the axis. Okay, well, this is the point of contact on the ground, and the wheel is rotating about that point of contact. The wheel is rotating about that point of contact. But for an axis passing through the center of mass, see, this is the angle through which the wheel rotated, and as the wheel rotated through that angle, it moved that distance, and that distance is equal to this distance, which is equal to r times theta, and that's what this equation is telling you. Okay. So theta is the angle through which, so you could mark a line on the object, and that's the angle through which it rotated. And if you take the time derivative of that, ds by dt gives you the velocity of the wheel, velocity of the center of mass, how fast the center of mass is moving, and d theta by dt gives you the angular velocity, the rate at which the wheel is spinning. Okay, so the linear velocity, the velocity of the center of mass, is related to the angular velocity of the wheel. So that's what that equation is telling you. And you can take a second derivative. Derivative of velocity gives you the acceleration of the center of mass, and if you take that derivative of that, r is constant for this wheel, and d omega by dt is alpha. So the center of mass acceleration is r times angular acceleration of the wheel. Okay, so that's what this equation is telling you. Okay, now let's go back to this slide. So rolling motion, okay, and we'd skip this slide. Okay, what this graph is, this picture is showing you is the following. So let me draw a wheel here. So here's a wheel that is rolling without slipping. So the wheel is rolling. So now if you put a light here, a light bulb here, let's say an LED bulb or something like that, you attach to the rim of a wheel, and as the wheel rolls, this will be the trajectory of the light bulb, and that's what's shown here. And that's the red curve, and this curve is a cycloid. The green curve is the green line is the motion of the center of mass of the wheel, and that moves in a straight line. Okay, and so that's what this diagram is showing you. Okay, so we saw that rolling motion rolling motion is a combination of translation, pure translation, and pure rotation. The sum of these two is this motion, which is the rolling motion. And so what this slide tells you is the velocity of the center of mass. Velocity of the center of mass is the radius of the wheel times the angular velocity of the wheel. So center of mass velocity is radius of the wheel times angular velocity of the wheel. And center of mass acceleration is r, the radius of the wheel, times angular acceleration. Okay, so that's what that tells you. Okay, so we've been saying that it looks like there's a question. Okay, no question. All right, so this slide, we've been saying that rolling motion is pure translation and pure rotation. So this is showing you the kinetic energy of the rolling wheel as the sum, the kinetic energy of the rolling wheel as the sum. This is pure rotational energy, and this is pure translational energy. Okay, it goes through the derivation. So when the wheel rolls, the point of contact on the ground, that is fixed, and the wheel is rolling over that point of contact, and then you get a new point of contact that goes at rest, and that rolls like that. And so that's how the wheel rolls. And so this expression is valid for a wheel that is rolling without slipping. Okay, so here's a snapshot as the wheel is rolling. This point is moving the fastest, this point is moving in that direction, this point is moving like that. And the kinetic energy of this entire wheel is the kinetic energy of this piece plus the kinetic energy of this piece plus this piece and all. So, so the kinetic energy is written in terms of the moment of inertia about this axis times the angular velocity squared. And you can use the parallel axis theorem to write the moment of inertia about this point that point is equal to the moment of inertia about the center of mass plus mr squared plus the mass of the wheel times the radius squared. Okay, anyway, so from there you get this expression which says the kinetic energy is pure rotation plus the kinetic energy of pure translation. So so again, showing you that rolling is a combination of rotation and translation. Okay. Now, here's an interesting slide. So, so here's a wheel that's shown. So this could be a bicycle, and let's say you're accelerating. When you accelerate, so your center mass is accelerating. Okay. So as the wheel is rotating, what happens is the point of contact wants to slip. And what prevents it from slipping? It's the static friction force between the road and the tire that prevents it from slipping. Okay, so, and the only thing that is in contact with the wheel is the road, which is exerting the static friction force. And this static friction force is what is giving the wheel the acceleration. Okay, so for instance, if it was a perfectly smooth surface, so you imagine an iced pond and an iced wheel, and you would never be able to accelerate. So for instance, if your feet were perfectly smooth and you were on perfectly smooth ground, you wouldn't be able to walk and go anywhere. Okay, so you need friction to be propelled forward. Anyway, so it's the static friction force that accelerates your car, and the static friction force is equal to mass times the acceleration of center of mass. Okay. All right, so in this graph, now that we've seen rolling is a combination of pure translation and pure rotation. So what this shows you is, and I urge you guys to go to that simulation and play with this. What these three objects are They all have the same mass. They all have the same radius. This is a sphere, this is a disk, and this is a ring, as you can see. And so initially they all have the same potential energy. You start them off at the top of the ramp, and then you look for which one reaches the bottom first. So the question is, do they all reach the bottom of the ramp at the same time, or do they arrive at different times? Now it turns out that they do arrive at different times. So initial energy is just potential energy, and the final energy is the same. So initial energy, here's what happens, is potential energy, and final energy is kinetic energy. So except that the kinetic energy is, you saw that they're all rolling down, and all these objects are rolling down, and kinetic energy is the translational energy plus rotational energy. Okay. So essentially the problem is the following. So depending on the moment of inertia, the larger the moment of inertia, the greater the rotational energy. The greater the rotational energy, less the kinetic energy, translational kinetic energy the object will have. And less the translational kinetic energy, the longer it takes for it to come down. Okay, because its velocity is lower, center of mass velocity is lower, and the longer it will take up. Okay, so it turns out, so the largest moment of inertia, the highest moment of inertia will be last, will take the longest. Okay, and you guys can look up the moment of inertia. Okay, so the moment of inertia of this is 1/2 m r1 plus r2 square. R1 and R2 are the two radii. The moment of inertia of this guy is 1/2 mr square, and the moment of inertia of this guy is 2/5 mr square. Okay, so it turns out that the moment of inertia of this guy is the greatest, so he will reach last. So this guy will reach last, and the moment of inertia is, this guy is higher, so this guy will reach first. Okay, anyway, I urge you guys to go to this simulation and play with it, and you'll figure all that out. Okay, and the next slide shows you that. Okay, so in this slide, as this object rolls down without slipping, so here are the forces. Here is the component of gravity, mg sine theta. Here is the friction force, static friction force. And what this equation says is this force minus this force is the net force on this object, and that's equal to mass times the center of mass acceleration. So there's Newton's second law applied to that. And this is, we'll calculate the torques about this axis, and the torques about that axis is the friction force times the radius of the wheel, and that's equal to the moment of inertia. So this is Newton's second law for rotation, rotational motion, because as it's rolling down, it's rotating about that axis as well. And well, so we're calculating it's rotating about this axis, so we're calculating the torque and moment of inertia about that axis times alpha. Okay, so combining these two equations, you can solve for the center of mass acceleration, and the center of mass acceleration is given by this expression. Now here, this expression is interesting. If an object was just sliding down without friction, its acceleration would be g sine less by this factor. It's g sine theta divided by this factor. Okay, and greater this is, smaller the acceleration. Okay, so an object rolling down the incline will have an acceleration smaller than an object sliding down without friction. So that's what this expression tells you. And this slide gives you the final velocity of the object at the bottom of the hill, at the bottom of the ramp. and h is the height of the ramp, g is the acceleration due to gravity, and I center of mass is the moment of inertia of these objects about the center of mass axis. And you see that greater the moment of inertia, smaller the velocity. And this guy has the greatest moment of inertia, this guy is next, second, and this guy is the smallest moment of inertia. So this guy will reach the bottom first. Okay. All right, so that covers rolling motion. So we have talked about rolling being a combination of pure translation and pure rotation. Okay, so I'll pause now and give you guys a chance to ask questions.